by just ordinary chemical processes. And then inflation takes over and magnifies this tiny, tiny region to become large enough to include everything that we see. And in the process of that magnification, everything happens the same way at all points in space. So the uniformity that was established originally is preserved by this humongous expansion of the inflationary period. So inflationary cosmology gives a very natural and simple explanation for why the universe is the same in all directions as we see it. OK, that was number one. Problem number two is the mass density problem. What makes the mass density of the universe what it is? And inflation gives an answer to that. In inflationary models, almost all of the matter in the universe, everything except what might have been there when it was 10 to the minus 28 centimeters across, which is assumed to be extremely small, almost all of the matter is produced as the inflation takes place. And that means you can calculate how much matter is going to be produced, because you understand the physical process by which it was produced. And the calculations show that inflation produces just the right amount of matter to drive the average amount of matter per volume, the density of the universe, to a particular value, which happens to be called the critical value. If you know about geometries of universes, this critical value is what produces a universe which is just on the borderline between being open and closed. But it doesn't really matter for our purposes that whether or not that you know that or care about it. The important point is that it makes a prediction for the mass density. And that prediction works incredibly well. Now, it didn't always. About 10, 12 years ago, astronomers thought that the actual density was only about 0.2 or 0.3 times this number, this critical density that inflation was predicting. Now that was uncomfortable. It was particularly uncomfortable for me because it meant that whenever I had dinner with astronomers, they would sort of look at me slyly and say that, well, you know, inflation is a very pretty theory, but you know, it can't be right because it predicts that the density of the universe should be this critical value, and we know it's not. It's only 0.2 or 0.3 times that. But all that has changed. Now I can have dinner with astronomers again because the measurements have changed. They discovered a new component to the matter of the universe. And now the experimental number, the observational number, agrees with the prediction of inflation to the accuracy that they can measure it, which is an accuracy that's a little better than 1% accuracy. So everything has fallen into place now. And the mass density that inflation predicts is just right. This new ingredient is the stuff that's called dark energy, which I'll be talking about very shortly. So I won't try to explain right now what it is exactly. But that's what changed the energy balance, putting everything into agreement. And finally, I told you there were three features of our universe that make our universe look like it came from an inflationary past. The third that I want to talk about is the small-scale non-uniformity. Now, I already told you that on very large scales, the universe is just unbelievably uniform, same in all directions to 1 part in 100,000. But nonetheless, astronomers can measure this cosmic background radiation, mostly through satellite experiments, to extraordinary accuracy these days. And at the level of 1 part in 100,000, there really are non-uniformities, ripples in the temperature pattern that they can measure. And those non-uniformities we think are actually crucial to the evolution of our universe. They're not just some side effect. We know that galaxies somehow formed after the Big Bang. And we think that these ripples really are the seeds for that galaxy formation. The way it works is that immediately after the Big Bang, these ripples tell us that there were some places where the matter density was a little higher than other places, only by 1 part in 100,000. It was a very small effect shortly after the Big Bang. But even this very small effect means that in regions of space where the matter density was just a little bit higher than average, that would create a slightly stronger than average gravitational field pulling matter into those regions. And that would then produce a still stronger gravitational field pulling in more matter. And all the structure in the universe, we believe, formed by these instabilities. The fact that when matter starts to collect, it pulls in more matter, resulting in galaxies, which then splinter into stars and ultimately planets and eventually even people. So these ripples are crucially important, and we see them and could measure them. The question is, where did they come from? In the context of conventional cosmology before inflation became part of the picture, there was really no answer to that question whatever. The uniformity was not understood, so it was just put in by hand. That is, one just assumed that the universe started out unbelievably uniform. But then you realized it couldn't be completely uniform, or you'd never get galaxies. So people had to just imagine that there was some set of non-uniformities that were there from the beginning at the level of 1 part in 100,000 that nobody knew where they came from. In inflation, we actually have an answer to that question, and the answer seems to agree with what we see. The inflationary solution is actually rather bizarre. Inflation attributes these ripples to the fundamental nature of quantum physics. As you probably know, the physicists are convinced that the world is really described by quantum theory and not by classical mechanics. And quantum theory is fundamentally a probabilistic rather than a completely predictive theory. So in this case, the classical version of the theory is predicting that the mass density of the universe would be completely uniform, this critical value. But when you put in the corrections associated with quantum theory, you discover that this classical prediction is really just the center of a probability distribution, because the quantum mechanics never gives you a definite number. It always gives you a probability distribution. So the quantum mechanical version of inflation would say that on average, the mass density of the universe is equal to this critical value. But some places it will be a little higher, just by chance, by the probabilistic nature of the underlying theory. And other places it will be a little bit lower, again, just by chance, due to the probabilistic nature of the fundamental quantum mechanics. And that's exactly the kind of pattern that we see, almost uniform, but with small ripples. And we can actually be quantitative about this. The details depend on details of the inflationary model, which we don't really know for sure. But nonetheless, it turns out that a whole big class of the simplest versions of inflationary models make the same predictions for the spectrum of these density fluctuations. And that then becomes sort of the prototypical prediction of inflationary models. And the surprising thing is that it works. That prototypical prediction, the generic prediction, in fact agrees beautifully with what we observe. And I'll show you some data in a minute. Let me just maybe clarify the use of the word spectrum here. We're used to the word spectrum, I think, in terms of sound waves. When we talk about the spectrum of a sound wave, we're talking about breaking up the sound wave into all of its different frequencies and talking about how much intensity there is for each frequency. In the early universe here, talking about the cosmic background radiation, we're doing essentially the same thing, but you should think of it in terms of wavelength rather than in terms of frequency. You could just as well, for sound waves, talk about breaking up the sound wave pattern into different wavelengths, because wavelengths are related to frequencies. And you could talk about how much energy there is for each wavelength. The reason why it's important to use wavelength rather than frequency is that for the cosmic background radiation, we don't observe it long enough to see it oscillate, but we do see wavelength. So we can talk about how much intensity there is for each wavelength. And the data agrees beautifully with what is predicted by inflation. The best data that we have today comes from the satellite called WMAP, the Wilkinson Microwave Anisotropy Probe, named for David Wilkinson. The satellite, by the way, has a very interesting orbit, which you might want to look up and pursue sometime. It's at a place called L2, a Lagrange point, L2. And the feature of L2 is that it doesn't exactly go around the Earth. What it really does is the Earth and WMAP, that's the Earth here, and that's the Moon, and that's WMAP. WMAP and the Earth go around the Sun together, with WMAP always on the far side of the Earth from the Sun. And that is a fantastic place to do astronomy, because it means that WMAP can look out on half of the sky this way, and everything that might interfere is on the other half of the sky. The Earth, the Sun, and the Moon are all on this half of the sky. And that relative orientation is maintained as the satellite goes around the Sun. So at all times, the satellite has a completely unobstructed view of half the sky. And over the course of the year, it can see the whole sky. So it's a wonderful place to do astronomy. There's now a new cosmic background radiation satellite at L2 called PONC,